think the good news is that this introductory section about game theories everywhere is not such an important part of the lecture, so you can live without it. Okay, so here's the model. Let's assume that person must decide if she should wear a mask. Everybody doesn't like wearing a mask, but wants to be safe from COVID-19. So, and let masks be effective only as a source control. So they don't really protect people wearing them, but they protect other people around. I think all these assumptions are pretty realistic, right? Usually people don't like wearing masks, especially people wearing glasses as so it's not very convenient. But we would love to be safe from COVID-19, and seems like masks are more effective as a source control and not as a personal device defending yourself. So let's assume that the utility of every person is U equals number of people wearing masks multiplied by 0.1 minus 10 multiplied by 1 if you wear a mask yourself, and 0 if you don't wear it. So the idea behind it is that every person gets a small increase in utility from every person wearing a mask, but a large decrease in utility, then he or she must wear it yourself. So basically, every time you put mask on, you create some pretty big costs for yourself, but small benefit for everybody around. So maybe there are hundreds of people around you, and you give small benefit to every person. So you're not really saving the humanity, but you helping every person just a bit. So now let's say, I think it's clear that the most important part here then is the number of people, right? So let's say there are 150 people. If everybody wears a mask, the utility of everybody's utility is 5, right? If nobody wears a mask, everybody's utility is 0. You can see the calculations, right? So this part, left part, is the benefits you create for everybody by wearing a mask, and this part is costs for you personally for wearing it. I mean, these benefits are created by all people for everybody when they wear the mask. So I have 2 questions. The first is it a game? What do you think? Is it a game?
It seems to be a game.
Why?
Because I'm influencing all the people around, and I'm aware of it, and other people are also influencing me.
So our payoffs are results of actions of all players. So all people are players, and payoff of every person, his utility or her utility, is the result of actions of all people around. So what outcome do you predict?
It looks like nobody will wear a mask because he or she gets no personal benefits from himself or herself wearing a mask, and other people wearing a mask doesn't depend on him or her wearing a mask. So there would be 0 utility for everyone, I guess.
Yeah, so this is a Nash equilibrium on this game. It's a bit complicated to prove mathematically because we have like many players, right? But intuitively, I think it's clear that if people care only about their own utility, the result would be not Pareto optimal. So it somehow reminds us prisoner's dilemma, and it is actually a prisoner's dilemma for n players. Prisoner's dilemma is a situation with 2 players, and here we have many players, but it's basically the same story. This kind of game is called the tragedy of the commons, and classical description of it is that people can use some common resource and they can take a lot of it, or they can take less. And if you take a lot of common resource, you benefit yourself, but you create small costs for everybody. And if a lot of people behave this way, these common resource get depleted and basically destroyed. There is a very famous book by Eleanor Ostrom. She was a political scientist and she got Nobel Prize, I think, maybe 10 years ago. This link leads to PDF, actually. So maybe some of you even read the book. It's translated into Russian. It can be really interesting to this. First of all, it's not very mathematically complicated. And it also shows how real life and game theory are related. So of course, real life is much more complicated, and society has created some mechanisms, some institutions, some rules, how to regulate this problem. And it's really interesting to read in this sense. Okay, so we are done with this section about game theory everywhere. So now to the topic of the lecture, and the topic is mixed strategies. So here is the game we discussed several times called Battle of Sexes. The settings is a bit different. So now our husband and wife choose between football and opera. But again, wife prefers opera, husband prefers football, but they would prefer to meet each other. So let's analyze the outcomes. So if husband goes to football and wife goes to the football, it's the best outcome for husband. He gets 3 units of utility, his payoff equals 3. And it's not the best outcome for wife. She gets just 1. The opposing outcome is if they go to the opera. So husband goes to the opera and wife goes to the opera, then husband gets 1 unit of utility. He doesn't really like opera, but he is with his wife at least. And wife will get 3 units of utility. And if they don't meet, they get zeros. It's a bit simplified story. So we have 2 pure strategies available to both players. The first strategy is to go to the football match, and the second strategy is to watch opera. But what if husband just tosses a coin to decide whether to go to the opera or to football? So this is a mixed strategy. So the idea of a mixed strategy is that there are some probabilities associated with pure strategies. So if husband just tosses the coin to decide, then he'll play football, play action football, that is to go to the football match with probability 1 second, and he'll go to the opera with probability 1 second. So that's the idea of mixed strategy. Here's formal definition. So suppose a player has m pure strategies. So again, it's possible for players to have many strategies. We just usually discuss very simple cases. We have just 2 pure strategies, but in a game, player can have many strategies, hundreds maybe of them. So a mixed strategy for this player is a probability distribution over his pure strategies. Probability distribution over his pure strategies. That is, it is a probability vector. Look, for every pure strategy, we have associated probability. So for strategy 1, we have P1. For strategy 2, we have P2. For strategy M, we have PM. So if we have 10 strategies, we have 10 probabilities. If we have 100 of them, we have 100 of probabilities. Of course, probability of a particular strategy cannot be greater than 1, or cannot be less than 0, first of all. It cannot be less than 0. But it can be equal 0. It means that player in this mixed strategy, player never plays this particular strategy. So it's possible for P equals 0 for a particular strategy. And sum of probabilities equals 1. Again, it's a very natural thing, right? So we assume that sum of probabilities equal 1. Very important part here is how we can evaluate payoffs in mixed strategies. When we were talking about pure strategies, we were always comparing strategies. We were talking this particular strategy is better than this particular strategy. How? By comparing payoffs. We compare payoffs. For example, if we have a dominant strategy, we can say this strategy always gives us higher payoff. That's why it's dominant, and rational player will always play it. With mixed strategies, we need another idea called expected utility. Is it familiar, expected utility? Maybe from microeconomics, maybe from finance. Does it ring a bell? Expected utility. It's pretty simple idea. Let's say I can give you a choice between two things. The first thing, I can just give you 100 rubles. Unfortunately, not in real, just as a hypothetical example. So I can give you 100 ruble, or we can play a similar game. We can play a game. I will toss a coin. If you get heads, I will give you 0. If you get tails, I will give you 200 of rubles. So you have the choice between two things: to get 100 rubles for sure, or to get 200 of rubles with probability 1 second. So for a person who is neutral to the risk, this is the same. So these two things, to get 100 of rubles for sure, and to get 200 with probability 1 second, they are the same. So expected in the first case, we have a fixed utility of 100. In the second case, we have expected utility of 100 calculated as 0 multiplied by 0 rubles multiplied by probability 1 second plus 200 rubles multiplied by probability 1 second. That is 100. So this is the formula for the expected utility, and this idea will be very important in this topic. So how we can use the expected utility theorem? It's basically a weighted average. It's a weighted average, and weights are probability. So we weight the payoff to each pure strategy by the probability with which this strategy is played. We weigh the payoff of each pure strategy by the probability with which that strategy is played. And then we just add up the weighted payoffs. We just add them up.
Excuse me.
Yes.
By payoffs of strategies, we mean like the sum of all payoffs in one strategy? Say player 1 has 3 strategies and player 2 has 3 strategies as well. So, and expected payoff for the players 1 strategy 2 is the sum of 3 payoffs in this strategy weighted by
basically sum of all possible payoffs. So if we have 6 outcomes in the game, there are 6 payoffs. It's a sum of 6 payoffs. You'll see it. But of course, if some probability is played with some strategy is played with probability 0, then this payoff equals 0. So some of them can kind of disappear, but in the formula we have all outcomes in the game. You'll see it in an example in a second. So the same game of battle of sexes, and let's say husband's mixed strategy is 2 seconds of football and 1 second of opera. So look, they sum up to 1, right? So usually he chooses football, but in 1 case out of 3, he can choose opera. And wife's mixed strategy is 1 multiplied by f. So she plays football with probability 1. You can say this is not a mixed strategy, this is a pure strategy. But does it follow the definition? Well, yeah. Based on this definition, pure strategy is just a special case of a mixed strategy. Pure strategy is just a special case of a mixed strategy. Then 1 strategy is played with probability 1, and all other strategies are played with probability 0. So we have exactly this case. So F is played with probability 1, that is always, and O opera is played with probability 0. So we have 4 possible outcomes, right? But if wife plays opera with 0 probability, we can forget about these 2 outcomes, right? The likelihood that by some reason we will be here is 0, and likelihood that we'll be here is also 0. So we need to discuss likelihood of just 2 outcomes, this one and this one. So likelihood that both spouses, I pronounce this right, go to the football game is probability of husband chooses football, that is 2/3, multiplied by probability of wife choosing husband, that is 1. So it's 2/3. So now we're talking about this outcome, probability of husband going to opera by himself. Kind of funny outcome. So this is 1/3. This is the probability that husband will choose opera, multiplied by 1, because wife always choosing football. So it's 1/3. So we found probabilities of or likelihoods of particular outcomes. So now we just need to multiply this probability to the outcomes. So husband will get 3 with probability 2/3 and 0 with probability 1/3, and it equals 2. So this is an example how we can calculate expected payoff of players in using mixed strategies. What about a bit more complicated case? So now our wife, or not our, but now the wife also mixes strategies. Now wife also mixes strategy. So half of the time she chooses football, half of the time she chooses opera. So how to calculate payoff now? So look, this is basically what you asked me about, right? So here we have 4 parts in this formula. Every part is 1 particular outcome. So husband can get 3. He will get 3 if he'll choose football and wife will choose football. Probability that he will choose football is 1/3. Probability that wife will choose football is 1. Football was for him 2/3, sorry, and for wife it's 1 second. So if you multiply them, we'll get 1/3, right? Is it clear? This idea of expected utility, is it clear?
Approximately, yeah.
Excuse me, can you explain one more time from where we take this like 1/2 and 1/3 and like this?
If you're talking about these probabilities, they are just given to us. If you're talking about this one, look, why we can be here? We can be here if husband will choose F and wife will choose F. That's why both probabilities are important. Probability of husband choosing football and probability of wife choosing football. So we just multiply their probabilities. So we multiply 2/3 and 1/2. It's 2/6. That's 1/3.
Excuse me, can we go to the previous slide, please? Yeah, you thought that 2/3 means that husband chooses football in 2 cases out of 3, right?
Right.
Doesn't it mean that 1 in wife's mixed strategy means that she chooses also football in 3 cases out of 3?
Right.
Maybe I'm a bit confused, but according to the table, she doesn't want to go to football. No, I mean.
Yeah, but we have these probabilities out of nowhere. Let's say they are just given to us. I'm not saying they are playing irrational. We'll find Nash equilibrium and mixed strategies. This is a prediction what rational people will do, but I got your point. So you're basically saying it's kind of stupid for her to play this. You're right, but it's just given to us. It's just exercise for us to check if we can calculate expected utility.
Okay, thank you. Now I get you.
Okay, so this idea of expected utility will be very important, or expected payoff will be very important for us in this topic. Okay, let's continue. Now we are ready to discuss Nash equilibrium. But first of all, let's talk about mixed extension of game. So mixed extension of a game is the game where a set of pure strategies extends with all possible mixed strategies. So think about it. In a very simple game with just 2 pure strategies, there is infinite number of mixed strategies, right? Billions and trillions of them. So in this case, pure strategy is a special case of mixed strategy with degenerated distribution of probabilities, as one particular strategy is played with probability 1. So it's always played, as in the case about wife always choosing football. So Nash equilibrium and mixed strategies is a Nash equilibrium in a mixed extension of the game. And John Nash proved, so this is his most famous result, that there is at least one equilibrium in mixed extension of any finite game. That's pretty nice if you think about it, because we were discussing different solution concepts. We were talking about dominance, and we found that there are some games that you cannot solve the game by dominance. In some games you can use it, but sometimes you just cannot. We talked about safe strategies and minimax and maximin approach, and again, sometimes it doesn't give us any prediction. We used Nash equilibrium and pure strategies, and it's more powerful, but still there are some games then there is no Nash equilibrium at all. So wonderful thing about Nash equilibrium and mixed strategies is that it always exists. So for every game we can make some predictions. If mixtures are mutual best responses, then the set of strategies is a mixed strategy Nash equilibrium. So mixed strategy Nash equilibrium is such mixtures that are best responses to each other. So here's the game without Nash Equilibrium and pure strategies. I hope you remember it's a very simple game. It was played even in ancient Greece and Rome. And the idea is there are two players. You can show one finger or two fingers, and there is even player who wins if sum of fingers is even. For example, if both players show one finger, it's odd and odd, then even player wins because the sum is even. It's two. If one of players shows two fingers and another shows one, like here, then even player loses, so it's -1, and odd player wins, and it's a zero-sum game. So very simple game. So we can check one more time that there are no Nash Equilibrium and pure strategies here. So for example, let's do it by definition. So if we are here, does it make sense for one of the players to deviate? Well, yes. For odd player, it's better to change his strategy to even and get one. But if we are here, now there are incentives for even player to deviate and play one. But if we are here, now there are incentives for odd player to deviate and to get one instead of -1. So we go here. And now there are incentives for even player to deviate, to get one instead of -1, and we'll go here. So there are no Nash Equilibrium and pure strategies. We cannot predict how this game will be played. Can you predict how it will be played, by the way? So let's say you have to play it with your, I don't know, 5-year-old younger brother or nephew. So how would you play this game?
Randomly, I guess.
What?
Because randomly, I guess. Because
But with what probability?
50-50.
Okay, so and now will be mathematically proof that your strategy that you intuitively come up with is ideal strategy for this game. So I think this example is also can help you to come up with right intuition. So imagine you are playing this game against a mind reader, so some person that can just read your minds. So how can you avoid losing? But the best thing you can do is just flip the coin, and at best the mind reader could only win half of the time. So again, 1/2. So let's calculate expected payoffs. Let's start from calculated expected payoff. To make it a bit easier for you to understand what happens, I use colors. Maybe I should use blue here. So look, let's say red player chooses odd. If he plays odd, he will get 1 with probability Q, and he will get -1 with probability 1 minus Q, right? So basically his fate is being decided by blue player. So if I play odd, then what I'll get depends on what blue player will do. Blue player can play odd and can play even. So I forget about very important thing. We introduced some notation here. So P is probability for the red player to play odd. 1 minus P is probability for the red player to play even. Right? Because we have only two strategies, we can use this simple idea of 1 minus P. Probability of playing odd and even equals 1, right? So we do not have to introduce some special notation for even, because we knew that if odd is played with probability p, then even is 1 minus p. And q is probability of blue player to play odd, and then 1 minus q is his probability to play even. So we just introduced these numbers, p and q. Standard notation is p for the first player, raw player, and q is for the second player, common player. So let me go back to discussing POs that we can get. So if I play as a raw player, if I play P, I will get 1 with probability Q, and I will get -1 with probability 1 minus Q. So the payoff associated with me playing this probability is 1Q minus 1 minus Q multiplied by 1. If I'll play even, then I'll get -1 with probability Q and 1 with probability 1 minus Q. So the payoff, expected payoff associated with me playing this particular strategy is -1 multiplied by Q plus Q minus Q multiplied by 1. These numbers are payoffs. These Q and 1 minus Q, they are probabilities for blue player. We can write down the same thing for column player. It's just this number should be blue, right? So there is quite a simple algorithm for finding mixed strategy in Nash Equilibrium in this very simple game of just 2 players with just 2 strategies. So these 2 parts, they are pretty simple, and we already did it. So we can write down expected payoff of a particular player as a function of probabilities. So we've done it here, basically. So my payoff depends on probabilities and probabilities of another player also. If we are talking about my payoff of playing odd, well, let's say I don't mix, I play pure strategy, but my opponent mixes strategies. Then my payoff of odd depends on these numbers and probabilities of my opponent, right? So that's what we have here. The first part is crucial. The idea is that in Nash Equilibrium, I mix strategies because they give me equal payoff. It's very important to understand it. Look, if one expected payoff of playing one strategy is higher than expected payoff of playing another strategy, what's the meaning of playing mixture? I just should play pure strategy that gives me higher payoff, right? So in this case, we can say that pure strategy dominates mixed strategy because payoff of pure strategy is higher than expected payoff of a mixed strategy. So the only situation that it makes sense to mix, it's a situation that expected payoff of one strategy equals to expected payoff of another. And please remember that these expected payoffs, they depend on what my opponent do, right? My opponent does. So again, let me repeat it one more time. I mix strategies only if my expected payoff of playing pure strategies equal to each other. So in this case, it makes sense to mix. Because if expected payoff of one pure strategy is higher than expected payoff of another pure strategy, I should just play one pure strategy and do not mix them. So this first part is important. So this is our game, and let's solve it for player one. So for player one, expected utility of playing odd equals to 1 multiplied by Q. So raw player will get 1 with probability Q plus minus 1 with probability 1 minus Q. So it's here. So if we simplify, it would be 2Q minus 1. Expected utility of playing even is a minus 1 with probability Q plus 1 with probability 1 minus Q. And if we simplify, we'll get 1 minus 2 multiplied by Q. So in Nash equilibrium, expected utility of both strategies should be equal. So I set them equal. I solve this equation, and I find I find a probability for the second player. That's kind of interesting. I set expected utilities for the first player equal. So I was talking about expected utility for the first player, but what I found is probability for the second player. Why? Because, well, the first player responds to the actions of the second player. So that's the case, then it makes sense to mix for the first player. If the second player plays with probability 1 second, it means second player plays odd half of the time and even half of the time. And we can do the same for second player. Look, similarly for second player will get, I think I have a mistake here, funny. Of course, it's a zero-sum game, so I should have the opposite numbers. I should have the opposite number, right? So he gets minus 1. If first player plays odd, he'll get minus 1 with probability P and 1 with probability 1 minus P. It's a zero-sum game. And he'll get, if he plays even, he'll get 1 with probability P and minus 1 with probability 1 minus P. Right? So in equilibrium, they are equal to each other. And if you solve it, you'll get, even though I have a mistake, the answer is right. And that's why I haven't corrected it, but I haven't paid attention to it. So they mix their strategies with probability 1 second. So there is no, sorry, where I am. So there is no pure strategy Nash equilibrium in this game, but there is Nash equilibrium and mixed strategies. Do you have any questions? Maybe I should go here. It's like the most important part.
Can you please repeat where in the next slide there is a mistake exactly?
I corrected. I will upload slides we've corrected. My mistake is that this is a zero-sum game. It's a zero-sum notation. So payoffs for the second player is not 1, but minus 1. Not minus 1, but 1. Right? So second player will get minus 1 if he plays odd. If second player plays odd, then he'll get minus 1 with probability P and 1 with probability 1 minus P. I corrected, and I plotted in a corrected way. So this is Nash equilibrium. And I hope you remember that Nash equilibrium is a set of strategies. Set equilibrium is not an outcome. it's a set of strategies. Nash Equilibrium and mixed strategies is pure strategies with associated probabilities. So in Nash Equilibrium and mixed strategy, a red player will play odd with probability 0.5 and even with probability 0.5. And blue player will play odd with probability 0.5 and even with probability 0.5. That's it. Let's apply the same approach to Battle of Sexes. So we'll use the same notation. So P is probability for husband to choose football, and 1 minus P is probability for husband to choose opera. Q is probability for wife to choose football, and 1 minus Q is probability for wife to choose opera. And let's calculate expected utilities for husband. For expected utility of playing football for him is 3 multiplied by Q plus 0 multiplied by 1 minus Q. Expected utility for him to play opera is 0 multiplied by Q plus 1 multiplied by 1 minus Q. If we set this expected utility equal, we'll get Q equal 1/4. So it means that in equilibrium, the husband will choose, no, the wife, it's about wife, right? Q is the probability for wife. In equilibrium, wife will choose football 1/4 of the time and opera 3/3 of the time. And similarly for wife, expected utility of choosing football is 1 multiplied by P and 0 plus 0 multiplied by 1 minus P. So this is expected utility of choosing football. And expected utility of choosing opera for her is 0 multiplied by P plus 3 multiplied by 1 minus P. Again, in equilibrium, we can set them equal, and it will give us P star equals 3/4. And 3/4 is probability of choosing football for husband, right? So he will choose football 3/4 of the time, and opera, I have belly here, sorry, with probability 1/4 of the time. So it's symmetrical, right? It means that usually they choose what they prefer, like 3/4 of the time they choose what they prefer, but 1/4 of the time they choose what another side prefers. Any questions?
Can there be predicted a solution of the game based on the mixed strategies?
But we've done it.
So the solution is that 1/4 is the probability of choosing a not preferred type of activity.
Yes.
Thank you.
So the solution is pure strategies with associated probabilities. So we can predict that in Nash equilibrium and mixed strategies, husband will choose football 3/4 of the time, and opera 1/4 of the time, and wife will choose football 1/4 of the time, and football 1/4 of the time, and opera 3/4 of the time. Can we calculate payoffs? Like if you're talking about pure strategies, it's very easy to find payoff because you can just look at the table. But if we have some solution and mix strategies, it's a bit more complicated to calculate payoffs, because in all 4 outcomes are possible, right? So if they play their mixed strategies, all 4 outcomes are possible, just with different probabilities. So let's calculate expected payoff in Nash Equilibrium. So look, I have 4 parts here. So this is the first outcome, this one, the second, the fourth, and the fourth. So all 4 outcomes are possible. So we have 4 parts in formula associated with every particular outcome. So these numbers are payoffs for this outcome. So for husbands, they are 3, 0, 0, and 1. These are probabilities, and every outcome can happen if like both probabilities are important. Probability of husband, so he chooses football 3/4 of the time, and probability of wife, she chooses football 1/4 of the time, multiplied by payoff. This is where we are talking about this particular outcome. And the same for wife. That's probability of this outcome multiplied by her payoff, 1. Is it clear?
Yeah, it's clear.
I think it's pretty interesting that in mixed strategy, Nash Equilibrium, they receive lower payoff compared to pure strategy, Nash Equilibrium, right? Do you remember if we have pure strategy, Nash Equilibrium here? Can you find them? So do we have a pure strategy Nash Equilibrium on this game? Come on.
There are 2 equilibriums.
Right. There are 2 pure strategy Nash Equilibria in this game. They are football, and opera. So we can check, for example, for football, there are no incentives for husband to deviate because he can get only 0 instead of 3. And there are no incentives for wife to deviate because she can get only 0 instead of 1. And in a similar way, you can prove that opera is also Nash Equilibrium. So interestingly, it somehow reminds you probably Prisoner's Dilemma, because both players, it's kind of rational, right? So they usually choose what they prefer. But because they usually choose what they prefer, pretty often they can be here in these outcomes. Probability is pretty large for them to be in these outcomes. Okay, so the last part of today's class is mixed strategy as a best response. Mixed strategy as a best response. So mixed strategies are defined as distribution of probabilities, right? Expected payoffs are also can be represented as a function of probabilities, and we've done it already. Basically, we've described them as a function of probability. Like even here, expected payoffs depend on probabilities of both players. Then best response of the given player can be described as optimal distribution of probabilities and the given distribution of probabilities of other player. So think about it. My best response is what distribution of probabilities I choose. And I respond to another player distribution of probabilities. So basically, in this simple case, with just two players and two strategies, P is a function of Q, P is a best response, Q is a function of P, so they react to each other. They react to each other. So they want to maximize their payoff in this situation. And here, let's again discuss battle of sexes. So we have a solution. So the solution is husband will play football with probability 3/4 and opera with probability 1/4. And wife will play football with probability 1/4 and opera with probability 3/4. So let's discuss best responses. For husbands, if Q equals 0, so let's start from these extreme values of Q. So if Q equals 0, this is the case, then mixed strategy is actually pure strategy. So if Q equals 0, it means wife always play opera, right? So Q is a probability of wife choosing football. If it equals 0, it means 1 minus Q equals 1. That is, wife always chooses opera. So what is the best response for husbands if wife always chooses an opera? Can I hide? If you just look at the table in the matrix, can you give me the example, the answer?
Yes, the best response is opera because it gives husband 1 point instead of 0.
Right, so in this extreme case, if Q equals 0, then best response for husband is to play opera. And to play opera means 1 minus P equals 1, that is P equals 0, right? So if Q equals 0, then the best response for husband is P equals 0. Now let's discuss the opposing side, the opposite situation. Then Q equals 1. If Q equals 1, that is, wife always plays football, never play opera. So what is the best response for husbands? So what is the value of P? If Q equals 1, then what is the best response?
1.
Right. 1. Okay, so we can see that in these extreme points, if Q equals 0, then P equals 1. If Q equal 1, then P equal 1. At some particular value of Q, husband should switch from opera to football, right? So at what value will it happen? What do you think? At what value will it happen? Any ideas?
May you repeat the question?
At what value of Q husband will switch from opera to football? So look, at Q goes from 0 to 1, right? It exists in this interval.
0.5.
0.5? Don't hear, right? Why? Okay, I think maybe it's time for us to draw. You can, first of all, I can just send you the link So you can see it in the app, or you can just look at the screen and see me drawing. So here's the link. Okay, so where I am here. So let me open my tablet. Okay, so let's make a graph first of all. So let's make a graph. I use black color for it. So I'll draw it this way. And this axis is P, and this axis is Q. And they both exist only in the interval from 0 to 1, right? From 0 to 1. Maybe here. So our goal is to present the Q as a function of P and P as a function of Q. So let's start from the husband. Let's start from the husband. So for husband, he reacts to the Q, right? So I think we started here. We said if Q equals 0, P should be equal 0. So this is the best response. If Q equal 1, then P also equal 1. So somewhere there is a switch from 0 to 1. But where? Well, we actually solved it already. We found Nash equilibrium and mixed strategy. So it looks something like this. So we have 1/4 here. So basically, till Q is less than 1/4. Till Q is less than 1/4. It makes sense for husband to choose opera. That is, if Q is less than 1/4, and 0 is a special case of this situation, then best response is P equals 0. That is opera, right? If Q equals 1/4, and we just prove it, this is basically what we were doing just 10 minutes ago. Expected utility of opera equals to expected utility of football, right? What does it mean? It means that the best response is somewhere from 0 to 1. And if Q is greater than 1/4, then best response is P equal 1. That is football. So here's how it looks like. So these two parts, then husband should play pure strategy. So almost for every Q, husband should play a pure strategy, because one strategy gives him higher payoff than another one. But for one particular value of Q, 1/4, husband is indifferent between these two strategies. He can choose any probability. He can choose pure he can play pure football or pure opera because their expected utility equal to each other. He can mix them in any variant. So it looks like this. So what it is? This is the best response for husband. So husband chooses P as a reaction to the Q. So P is a function of Q here. Husband tries to maximize his welfare by choosing P. If you don't really trust me, you can check. You can calculate expected utility. So calculate expected utility of football and expected utility of opera for Q equal 1/5, like here. So based on the graph, we can predict that expected utility of football will be higher. So we predict that expected utility of football is higher, and that's why husband will not mix, he will always play football for this Q. But you can check if you don't trust. Okay, so this is best response curve for best response diagram for husband. So what about wife? Now we should do the same for wife. So let's use another color for wife. Let's use red. So now wife reacts to the P by choosing Q. So if P equals 0, what should be Q? Can you tell me? So if P equals 0, it means husband chooses opera. What should wife do?
Choose opera.
Yeah, so what is Q?
Is 1.
No, Q is the probability of wife
Q is
playing
probability of y. No, is 0 also.
football. Right.
Excuse me, why you put 1 divided by 5 above the 1 divided by 4?
Or where should I put it?
Below, no? It's less than...
Yeah. Maybe yes.
I meant, sorry, got it. I meant, that's funny. This is what I meant. That's kind of funny. So in this case, half of the time wife chooses opera and half of the time she chooses football. So what is our prediction? Well, 1/5 is also work here. It's just less evidence, I think, point to check. Okay, so it equals 0, right? It equals 0, so it's somewhere here. If P equals 1, that is wife, husband always choosing football, what should wife do?
Then choose football. Choose 1.
So we're here. So it's somewhat similar, right? So there is some value of P, and then wife should switch from opera to football, from football to opera. And again, we already calculated this value. It's 1/4. looks like this. And that's why this diagram is notorious. And students always make jokes about it. So it looks like this. So for a particular value of P, so we can write down it's like here. In a similar way, if P is less than 1/4, then best response is Q equals 0. That is football, right? Sorry, opera.
Can you explain why 1/4? Because we calculated it was 3/4, no?
Right. Thank you. Yeah, so they are not symmetrical in this case. For sure. Good news is that you follow them, if you correct me. Yeah, so at this value of P, it makes sense for her to switch. Because for other values, one pure strategy is always better than another. It gives higher payoff. There is no meaning in mixing strategies, right? They should not mix. They should just choose one pure strategy. Okay, so let's go back to the lecture. I think I have a couple of last slides. So if you look at this game, so again, we have 2 players and 2 strategies. And we have payoffs like 50-50, 80-20, 90-10, 20-80. And you can think about every player choosing probability as a response to another player's probability, right? So every player wants to maximize his payoff depending on what is the probability another player chooses. So here, for Q less than 0.6, best response is P equal 1. P equal 1. That is, always play the first strategy. At particular level of Q equals 0.6. Here, both pure strategies, the first one and the second one, they give the same expected payoff. They give the same expected payoff. So it's basically the first player is indifferent between playing first strategy or second player strategy or mixing them in any possible combination. Is indifferent because they are basically the same. They give the same expected payoff, and that's why P can be somewhere in this range from 0 to 1. And if Q is greater than 0.6, then again one particular pure strategy gives higher expected payoff than another one. That is, there is no meaning, there is no sense in mixing them. To maximize his payoff, the first player should choose just one dominant strategy. That is P equals 0. It means the first player will play second strategy in this case. He will play the second strategy. Right? In a similar way, we can analyze it for the second player. So here Q, here second player chooses Q based on P. So Q is a reaction for P, function of P. And if P is greater than 0.7, then the first player should play the second strategy. If P is less than 0.7, the second player should play the second strategy. But for particular value of P, where P equals 0.7, expected values, expected utilities, expected payoffs for the second player, payoff for the one pure strategy and another pure strategy, they equal to each other. That's why he can choose the first strategy, or he can choose the second strategy, or he can play half of the time the first and half of the time the second, or any possible mixture. He's indifferent between pure strategies and all possible mixtures. That's why Q is somewhere in this range from 0 to 1. So this is the diagram. So P goes from 1. So here, so this is graph for P, right? P equal 1 till Q equals 0.6. Then P switches to 0. So here P equals 0, right? Q equals 0 while P is less than 0.7. If P is less than 0.7, then Q equals 0. So here Q equals 0, right? Because again, we have Q here and P here, a bit misleading, but you'll see why we're doing it. So here Q equals 0. Here player is indifferent between two strategies. So Q can be any, basically. He can play Q equals 0, that is one pure strategy. He can play Q equal 1, that is another pure strategy. Or he can mix them in any possible combination here. And if P is greater than 0.7, then Q equal 1. And in this last graph, we put both players' best responses into one diagram. So now we have P here and Q here. So this is the same diagram, and this black one, we just switched it. We switched Q and P, and that's why it looks different. So this point, this is a Nash equilibrium in mixed strategies. Because I hope you remember that by one of the definitions, Nash equilibrium is then one player's best response is another player's response. So here, the second player's best response is best response for the first player. So this point are best responses of both players. There is no incentives to deviate because it's already best response. So it's a Nash equilibrium. I think we are done. So if you have some time, you can ask your questions. If you don't have questions, you can just leave. Thank you for the class. People who have questions. Any questions?
Could you explain once again how did we find this exact values where it is
0.6?
Makes sense to switch from?
It should go back to where we calculated Nash equilibrium and mixed strategies. And probably the most important idea is that in equilibrium, the expected utility of one strategy equals to expected utility of another strategy. Because look, if expected utility of odd is greater than expected utility of even, I should just play odd, right?
Yes.
So in this case, there is no mixed strategy. I just always play odd. So this idea is probably the most important. So they should be equal to each other. And here, like we calculated expected utility of playing odd for the first player, and we calculated expected utility of playing even for the first player. And they both function of Q, right? So if I play odds, I am at the mercy of player 2. Player 2 will decide what will I get by choosing Q. So we have Q here, it's a function of Q. So if we set equal these two expressions, we'll find Q. And this is the particular value of Q that where I'm indifferent between playing odd and even. So this is the only value of Q where we can play mixed strategies. And in a similar way, I calculated, although I have a mistake here, we can set equal expected payoffs for the second player and find P star. In a similar way here, set them equal. It's kind of what is complicated here for students is that I set equal payoffs of husband and find probability for wife. And then I set equal payoffs of wife and find probability for husband. But this is exactly because this is a game, right? My best response depends on other players' action. And this is why they are related in such a maybe weird way. Well, we'll have a lot of practice in the seminars. So you will practice and get more or less intuitive understanding of it. And also, I can recommend you one video. If you Google in YouTube, I think it's called Mixed Strategy Algorithm. Mixed Strategy Algorithm. There is a very good explanation. I think it's William Spanier. He has the whole course on game theory in YouTube, and video for mixed strategy Nash equilibrium is particularly good. It's quite short and I think contains pretty good explanation. Very similar to what I've tried to explain, but you cannot listen like me several times, and you can listen to him many times because it's a recording. Any other questions? Okay, if there are no questions, thank you for the class. See you next time. Bye.
Thank you. Goodbye.
Bye.